vector field of this function, which is x square y, which has an x component 2xy and x square is the y component, vector component that is being plotted here and has been shown, and we can get some idea about where does this goes to 0 or a maximum value is possibility somewhere here and somewhere here, which means if I try to solve this, okay, x0 and y0 seems to be the slope where maximum change that is being going to take place. You can see here, this is the curve or x square y, and you can see somewhere on this along the y, and suppose this is this, if you take it as x, this is y, and you can see this is the point and this is the line. This is the line on which you find the slope is going to be the maximum for this function x square y. I hope it's clear for you now. You can see here this is the maximum, and that continues along this direction. Okay, along this. A similar thing happens the other way also. You have this, and that's also continues on this. Okay, so now I have x square y gradient is now 2xy and x square. That's the plot and clearly indicates this line, and this line seems to have the delta t, or the gradient of this scalar is a slope that has a maximum value that can be seen here by plotting it again, norm of that vector, which is a gradient. You can see here this and this. Okay, that's how this is happening, and this is reflected in your vector field plot. Okay, minus xy. If I have a scalar, this is what your vector, and if I plot it, this is what the nature of the field that looks, and then again you can find out the norm and make a plot and locate where it has the maximum slope. That's also possible here. Okay, so this is how we will be understanding about the gradient operator, and that will be used further for various applications like number one, divergence, del dot v, which is most important quantity which you come across many places. Okay, divergence of a vector field can be represented like this, and this is how much the vector v spreads. This is going to be a scalar quantity at the end. So that's what the thing that you are going to get out of that. So geometrically it can be interpreted like this. Geometry, which means we represent in the form of a geometry and try to understand about this divergence through these pictures. There is a divergence, there is no divergence. PC, okay? They are in the same direction, there is no divergence. So geometric interpretation, the name divergence is well chosen for del dot v is a measure of how much the vector v spreads out, diverges from the point in question. For example, the vector function in figure 1.18a, that this is the figure, has a large positive divergence. If the arrow points in, it would be a negative divergence. If you reverse the direction here, it's going to be negative. This is positive divergence. Okay, so negative divergence. The functions 8.1b in zero divergence, and C again has a 1.18c, there's a divergence, positive divergence. Please understand that v here is a function. There is a different vector associated with every point in space. So that's clear indication. This is the magnitude are different, therefore it is a divergence. Whereas this fellow has the same strength all throughout. This fellow changes in magnitude, there seems to be change in the value of the divergence. Smaller, this is little bigger, and this much bigger. Therefore, they said there's a divergence associated with it. In the diagram, of course, I can only draw arrows at a few representative locations. Okay, so imagine standing at an edge of a pond, sprinkling some sawdust or pine needles on the surface. If the material spreads out, then you dropped it at a point of a positive divergence. If it collects together, you dropped it at a point of negative divergence. The vector function V in this model is the velocity of the vector at the surface. This is a two-dimensional example, but it helps give one a feel for what divergence means. A point of positive divergence is a source or a faucet. A point of a negative divergence is a sink or a drain. So sink, source, sink, drain, or a faucet. This is what the terminology that is being used. Okay, so now we can see you have a vector R. You're able to see this. R vector is represented as x with the unit vector x, y with the unit vector y. This is the VA vector, and this is VB vector, which is equal to Z cap, no other component. VC is Z with the magnitude with a Z cap. So there are three vectors. Now, what is the divergence of this? Okay, and we know what is the magnitude of this. X cap, Y cap, Z cap has been found. And you can see here that's going to be a finite magnitude of divergence that can be obtained by plotting it. Okay, taking the x, y, and the z as a function of x, y, z, and this is the divergence which can be felt in a three dimension. It is diverging out, starting from center in all the direction. Okay, this is how the vector field will look like. You can see the directional changes of the vectors. If you look at here, you can feel that it is trying to go diverging out all the possible directions because we have x, y, z independent components that are varying. Of course, this magnitude will be scaled. That's all. Okay, that will be only scaling factor. Okay, we're able to see that. And suppose you have been given length of this vector. Okay, you are asked to find out gradient. What would you get? If you understand what I'm asking now, what does it mean? I'm trying to say that there is a gradient. Yeah, gradient of the length of the vector is square root of get x square plus y square plus z square. This is the scalar now, and it has a component x, y, or the x, y, z is the variable that is varying, which is a length of a vector r. Agree with me? And I'm going to find the grade of this. What would you get? What is expected? Yeah. This is what the result, which is what I have written here, component. Okay, so I mean this scalar being converted into vector form. Okay, I think there must be some discussion about that. Maybe you can see that later stage. So it's so clear that this is along the r direction, there is going to be a maximum change. Okay, that's what it means here. And the gradient of this x square plus y square plus z square is this. This is the number that we have. And I'm looking for the divergence for such vector. It is expected to have this kind of magnitudes, and it can be represented like this. Okay, the vector field, it looks like this. If you call them as a displacement vectors, it's a displacement vector. It is acceleration means an acceleration vector. It can be any vector quantity. That doesn't matter for us. So divergence x, y, z is of course 3, and you can see the vector plot of 0, 0, 1. Okay, there's no component x and only z component that can be represented by looking at. You can clearly feel that yes, is a direction. There is a vectors which are shown here, and this is the vector field for this. Okay. Again, the divergence of this is equal to 0, there is no divergence. Equal magnitude, there is no divergence. Then the vector field of this is that again, what is it? Is it same? No. 3 dimensional vector minus 32 plus 3, which is only the vector points has been changed, or what is it? That's also same. So same thing which has been shown, vector plot 3D again that has been shown. Okay, so now divergence of this is equal to 1, because when you change the length, it changes. Now compute the divergence of these vectors. How do you do that? Compute the divergence of these vectors. So what you do, take the component of x square 3xy minus 2x. Okay, this is a vector. This is what your vector is. Does it have a divergence? The divergence goes to 0, which means there is no divergence for this kind of a field. Okay, which can be computed, it can be shown now. Similarly, vector field of what is it? xy, yz, and 3zx. So we find out what is the divergence for that. Divergence is for xy, yz, 3xy. In fact, I guess the 2. Am I right? Problem was 2xy, 2yz, and 3xz. I think that's something wrong. I think I have done it. Oh, this is different problem. And this problem is, what is this one? Okay, I think this is different. This is different. X square 3xz square minus 2xy, right? That's right. And we have found the divergence that goes to 0. Then second is xy and 2yz. That's missing here. Okay. 2yz and 3xz. So this is the field that you have. Okay. And what about this divergence of this? Definitely it has a divergence. There's a magnitude of 3x plus y to z. And that you wanted to see, probably that has not been plotted. You can plot this divergence now. You can plot the vector field has been shown. Divergence is equal to 0. Okay. So we are not plotting the. So now we have the fields corresponding divergence can be represented by just taking the divergence with respect to the corresponding variable, and it can be done in any coordinate system. It need not be here like what you have the so-called the Cartesian coordinate. You can have it on the spherical, cylindrical, any coordinate system. That can also be, this can also be plotted. Okay, the curl is this defined by this with operator. And this is what your expansion, which we represent in the determinant form. Find out the x, y, and z component. And it has been shown here, curl of Vx, Vy, and Vz with respect to x, y, z, because this Vx is a function of x, y, z, Vy is also a function of x, y, z, Vz also a function of x, y, z. Therefore, we will be considering all the derivative component of this, though V are a Vx, x, y, z, Vy also x, y, z, Vz also. You can see all the components in it. That has been found here, and you can compare this with this and confirm it. Yes, what has been given here, you are having same results here by taking a curl of Vx, Vy, Vz with respect to x, y, z. And this is what the result that has been shown in the text matter. This is actually the Mathematica code. When you ask to find out the curl, this is what the curl that you have. Okay, now find the curl of Vi equal to minus y x cap plus x y cap. Okay, minus y x cap It will be plotted, yes. Vector field of minus y plus x. And we are asked to find out what is the curve. So there is a curve, magnitude 2z, which is pointing along the z direction. You can see minus y plus x. The x component as a minus y component as a x. And if you take the curl of that, the curl direction is to z cap with the magnitude 2, which is perpendicular to both x and y cap, x cap and y cap. That's the direction of that. And you have another problem, b equal to x y cap. That has a z cap component. This is what you are told of that. b equal to x y, that is a component of x cap. Now, if you plot this as a vector field, you can see a minus y comma x 0, x y is like this, and z component is 0, and you can see they are circularity. Okay, so you can see that you can really feel that there is a field that is going around. Now this is in the anti-clockwise now. Okay, this is the anti-clockwise, and if you want to change direction, change this sign here, that corresponding changes. Okay, so this is for the minus yx that has a finite value of the curve, which means there is a rotational effect that could be seen, and geometrical interpretation goes like this here. Geometrical interpretation, the name curl is also well chosen for del cross v is measure of how much the vector v spiles around a point in question. That's three functions in figure 1.18 all have zero curl, as you can easily check for the reversal. Figure 1.18, previous one. The one which we have seen, there's no curl for this, all the three. There's no curl involved, there's no rotation of the vectors. So therefore, A, B, C, you can try that again, find out the curl for this functions, whatever has been given, the curl goes to 0. So that's what he is trying to say by referring those figures. Okay, all have a 0 curl, as you can easily check for this. Whereas function in figure 1.19 have a substantial curl pointing in the z direction, as the natural right hand rule would suggest. Imagine again you are standing at the edge of a pond, float a small puddle wheel, a car with toothpicks pointing out radially would do. If it starts to rotate, then you placed it at a point of non-zero curl. The whirlpool would be the region of a large curl. Whirlpool would be the region of a large curl. So rotational is possible to quantify by using this curl. Divergence can be quantified by using the L with a dot with a vector field. Okay, these are the things which is most frequently used in our physical problems. When you have a vector field or electric field or a magnetic field, okay, like that, there are so many things, so many places you would come across this. Okay, some of the important related things, important fundamental theorem. The fundamental theorem of calculus. Suppose f of x is a function of one variable. The fundamental theorem of calculus says integral a to b f of x dx, dou f by dou x dx equal to the value of the function at the end point. Okay, because this will disappear after integration and you will get a function back, and then f of x to be substituted with lower limit and upper limit, then the magnitude is equal to f of b minus f of a. In this, in case of this doesn't look familiar, I'll write in another way that f of x, this is dou f by dou df by dx is equal to f of x. This is equal to f of b minus f of a. That's what this function is. This is equal to capital F of x. The fundamental theorem tells how tells you how to integrate f of x. So you think of a function f of x whose derivative is equal to f, which means this f of x is the derivative of the f of x, small f of x. That's what it means. So when you have that, you just take the function which is having a derivative, and that derivative component has derivative function. Endpoint is enough for us to get the magnitude of this. That's what the theorem says. This is one of the most fundamental theorem, the calculus. Notice the basic format of the fundamental theorem. Integral of a derivative. Integral of a derivative over some region is given, over some region means A to B, is given by value of the function at the endpoints, boundaries. The vector calculus, in the vector calculus, there are three species of derivative. Three species of derivatives, note down. In vector calculus, there are three species of derivative: gradient, divergence, and curl. They are all derivatives. Correct? You can check that. Okay, confirm it. Okay, derivative. Gradient is also derivative. Divergence is also a derivative. Curl is also a derivative. And each has its own fundamental theorem with essentially the same format. Okay, essentially the same format. I don't plan to prove these theorems here. Rather, I will explain what they mean and try to make them plausible. Proofs are given in the appendix. Refer that Griffith book. He has given the proof there, but it's not the proof that is important, that you have to understand what is the theorem, what it means. That is important. So this is the case where you have a one variable. If you have more than one variable, then it becomes a sort of a vector like. Since it happens now, suppose if you have a scalar function of three variables starting at a point A, we move a small distance dl1. This is the dl1 which we are going to move. That is, this is a small distance that we are going to move. dl, which is a vector. According to equation 1.37, okay, the function t will change by an amount dt that we have already seen. This dt is equal to gradient of t dot dl1. And this is the sort of a single function, and this is the vector function which is in the xy direction, and you are moving starting from a position which is a vector to a b position, another vector. Starting from this point, you are taking this path. That's how you are moving. And each dl1, dl2, dl3, dl4 go on, and then make an integration. You'll get the value of the function. Let's see what's going to happen. Now we move a little further by an additional small displacement dl2. The incremental change in t will be this. Okay, in this manner, proceed by infinitesimal steps. We make a journey to a point B. Please note that this is A vector point, B vector point. At each step, we compute the gradient of t at the point and dot into the displacement dl. Okay, each point we will calculate and make a dot with respect to that. This gives us the change in t. Eventually, the total change in t is going to be A to B along the path selected. E is this one, which is going to be t of B minus t of A. This is the fundamental theorem of gradients. Like the ordinary fundamental theorem, it says that integral, here it is the line integral. It says that integral is a line integral of a derivative. Line integral of a derivative. Here the gradient. That's a derivative. So it says that the integral, here the line integral of a derivative, here it's a gradient, is given by the value of the function at the boundaries A and B. Value of the functions at the boundary A and B. What is the geometrical interpretation for this? Suppose we wanted to determine the height of a Eiffel Tower. We could climb the stars using a ruler to measure the rise at each step, adding them all up. Okay, that is left side of equation 1.55. This is the equation he refers. Or you could place altimeters at the top and the bottom, subtract the two readings. Okay, subtract the two readings. That is the right side. This is the right side, two readings. You should get the same answer either way. That's the fundamental theorem. So what is that? He's trying to say that you climb the stars using a ruler to measure the rise at each step, adding all up. Or you could place a altimeters on the top and the bottom, subtract the two readings. That is the right side. One is the going by steps, and this is going by a meter, measure the top and bottom, and then subtract it with the actual value what you want, and that should be equal. They both must be equal. That's the important point. Incidentally, as we find in exercise 6.1.6, line integral ordinarily depend on the path taken from A to B. So please note that. Incidentally, we found that the line integral ordinarily depend upon the path taken from A to B. But right side of equation 1.55 makes no reference to the path, only the endpoints. So eventually, gradients have the special property that the line integral are path dependent. That is the most important. Eventually, the gradients have special property that line integral are path dependent. Okay, line integral path independent. This B to A, you can reach B and A any way you like, any path. That's what the meaning of that. Okay, so now here A to B delta T is independent of the path taken from A to B. This is another corollary you have. Equal to 0, del dot of dl equal to 0. Since beginning and the end points are identical, this goes to 0. This happens. This is the property of the fundamental theorem of the gradient. Okay, and here is the example here, nice example. You can think about it. Let x equal to t equal to x y square. Take a point a 0 0 0 and b equal to 2 1 0. This is 0 0. Then this is 2 1 z equal to 0. That's the point. Okay, there are 2 points. A is this, B is that. Okay, check the fundamental theorem of gradients. What is the checking should be done? Find out left hand side, find out the right hand side, that must be equal. That's what the meaning of that. Okay, so like Eiffel Tower, how what that we have done. Same thing can be done too. Take a path now. Okay, or take a left hand side, evaluate it. So find out what is the del t dot dl for the function. Okay. So y equal to 0, dl equal to dx x cap. Okay. When you are moving along this path, y equal to 0, dl equal to dx into x cap. So therefore, del t dot dl equal to y square dx. That's equal to 0 because y equal to 0. Therefore, this goes to 0. So you can see how this path leads to that del t dot dl equal to 0. Path 1. Go to the path 2. This is the path 2. What is the path 2? Says that x equal to 2. dl is along the y direction. So dy into y cap. So now you find out what is del t dot dl. That dl has been already found. You have the del t which has been given by this because we know what is the function t. Del t can be taken, and your dl is dx, dy, dz. These are the line integral elemental length of the line integral that you have. The dz component is not there. So delta t into dl that has been 4 by dy 0 to 1. substitute, we get a 2. This is what your value of the function at the left hand side by moving from path 1 to 2. Okay. Now the total line integral is 2 by this process. We've done this systematically. You could get it. Now, in this, is this consistent with the fundamental theorem? Yes, you can check. T of B minus T of A. What is T? It's given already. X square. And you know what is the X and Y value at B and A. So, you substitute that. I'll get 2 minus 0 is equal to 2. That has been found by using this. Left hand side following del T dot dl for the path 1, del T dot dl path 2. And if you take the total value, that's going to be the value of the T of B minus T of A. Now, suppose if I take the path A to B, the third path, do I get the same result? You should be. Otherwise, this theorem is not correct. Okay, check it here now, whether that's going to happen or not. Now, just to convince you that the answer is independent of the path, let me calculate this same integral along the path 3. Straight line from A to B. Okay. So this line is y equal to half x is this. You can find out what is the equation for this. This is going to be y is equal to half x. Find out dy. Then you know what is the del t dot dl. Okay. Hello. This can be found easily for these points are given. And you can find out y equal to half x this relation connecting y and x. If I make a plot with respect to x and y, I'll get this line with the slope half. That's what is passing through the origin. It's like y equal to mx plus c, that c equal to 0, and this m is the slope which is half. That's what the relation is here. Now dy has been found. Del dot dl is already known to you. Substitute them. You find this is going to be 3 by x square dx. Integrate along the path which is 0 to 2, 3 by x square dx, and make a substitution, and you get the value 2. Okay. Del t dot dl is available. That should be integrated from 0 to 2 because by using these relations which you have, and you will end up with the number 2. This is also confirms that path 3 also provide the same results. Whether you go from here to here or you use the fundamental theorem of T of P minus T of A or the path 3, you have one and the same result, which confirms that this is the fundamental theorem. You can check with the number of problems that has been given. These are the problems which is given here, and the solution is available. You can check it. Okay. So I am not going to work it out now because everything is known to you and solution is also being given. One only thing you have to be carefully see the how mathematics has been implemented here. Okay. To find each time del t dot dl, del t dot dl, all the paths, what are 1, 2, 3. Here is 1, 2, 3 path. And you can have a path like this also. Okay. And corresponding is given. And the answer is very much consistent. You can see here. Okay. Which I believe I have done it already. No. Okay. So this is the we have taken the dot product of the gradient of this function. Okay. dx dy dz. Dot product has been taken. Okay, so this is what your fundamental theorem of a gradient, which is most important theorem, and you would come across a number of places in your physical science problems. You might have seen this is. Do you come across this anywhere? This kind of a thing. Did you come across this somewhere? In your mechanics, electricity, magnetism, Quantum mechanics, did you come across anywhere? No? Del T dot dl equal to 0 over a closed path. Yeah, anywhere?
Ambience law, sir.
Yeah, did you come across this any other place? For example, in mechanics also you have this. In mechanics, you do have this kind of a relation which says some fundamental physical process. No?
Not remembering, sir.
Not remembering. Okay, fine. See, work done by the force or a closed path. What is that? Work
Zero.
done 0. And work done is independent of the path. That is there in this first one. Second is closed path. It goes to 0. Then you connected the path dl and del t in your process. Okay. So can you tell me what could be the del T equivalent in mechanics?
Conservative force.
No, that's right. But you have a del T here. How do you connect it?
Gradient of potential.
That's right. You are right. Gradient of the potential is going to be a force. So force does the work, and depending on the nature of the path it takes, okay, it is independent of the path. A to B, if it is fixed, whatever the path if you take, this magnitude is same. If you do it over the closed path, work done is going to be 0. So that is where strong link that is happening in mechanics. There are several such places you would come across this kind of behaviors. Okay, therefore this is very, very important. It fundamentally speaks about the conservative force. Okay, energy is conserved and conservative force. And that is the case, this will be satisfied. Okay, fine. That's great, good. Now the fundamental theorem of divergence, what it says, which is equivalent to what you have here, whatever which is defined here. You are trying to interpret that. Where is it? Geometrical interpretation. Where is it? See? Like ordinary fundamental theorem. Ordinary fundamental theorem is df by dx, what he's trying to say. Like this, you can describe this also, nothing great here, that this is what he is describing here for the fundamental theorem. Like ordinary fundamental theorem, it says that the integral, here the line integral, this is the integral of a derivative is going to be your gradient, is given by the value of the function at the boundaries, okay, which is a and b. That's what the description for this. It's very easy to, you don't have to even memorize. If you know this equation, you can write it this thing automatically. Like an ordinary fundamental theorem, it says that the integral, you are claiming integral here, and we can write it within the bracket. Here is the line integral, okay, of a derivative. This is the derivative. Here the gradient, okay, is given by the value of the function at the boundary a and b. Now come to this next part of it. You would see that similarity can be seen. You can see the fundamental theorem of divergence states that in honor, I suppose it is a great importance. This theorem has at least 3 special names called Gauss theorem, Green's theorem, and or simply divergence theorem. Like the other, the fundamental theorems, like the other fundamental theorem, it says integral of a derivative, see, integral of a derivative, in this case divergence. It's a derivative only, but it happens to be divergent. That doesn't matter. Integral of a derivative, in this case divergence, over a region. Instead of a line, it is going to be over a region. In this case, volume. The previous case, it's a line. In this case, it's a volume. That's all. Correct now? Say that integral over a volume, integral over the volume B is equal to value of the function at the boundaries. In this case, surface S that bounds the volume. There, the value of the function at the endpoints A and B Here it is the value of the function at the boundaries of the surface. Okay. Notice that the boundary term is itself an integral. That's the difference. Whereas in the previous case, you have a final value, but here it has an integral form because volume and surface are connected. Okay, and the value is found to be the boundary of the surface, yes, that bounds surface, yes, that bounds the, in this case, the surface, yes, that bounds the volume. Notice that the boundary term is itself an integral, specifically a surface integral. This is reasonable. The boundary of a line, okay, is just endpoints, but the boundary of the volume is a closed surface. Is it not? That's also correct. But the boundary of a volume is a closed surface. That's what the meaning of this. Okay, so which means this V vector, it sits here, dot dA surface integral. If I combine it with the gradient, in this case happens to be divergence, integral over the volume, I have the so-called the fundamental theorem of the divergence that you will be getting it. Okay, volume connecting to the surface integral. The previous case, line integral connected to the endpoints. All the wordings, everything same, only replace it by the integral of a derivative, in this case divergence. Over region, in this case volume, is equal to value of the function at the boundary, in this case surface, yes, that bounds the volume, that's all. This is a consistency in understanding the process. Only there is an additional integral because it happens to be a surface. We are putting a V dot dA. Please note that dA vector is a surface vector. Okay, it's not like a line, it is a surface. dA is a surface. Okay, elemental area or a unit vector on the surface. Okay, this is the dA. This is d tau, which is a volume, del dot P. So now we are going to see, please look at this analogy between this and this. They are one and the same, except that instead of endpoints, I have a surface bound by this volume integral. Okay, and del dot V d tau, replace this V should come on this side, like what you have in the T, capital T, that's coming on the other side with the n value. See, coming here. Same thing here. Del dot V, that V should be appear here. So V should be sitting there as a common factor. The volume integral and surface integral being getting connected. That's what your Gauss theorem or Green's theorem or divergence theorem. So let us look at the geometrical interpretation. If V represent the flow of an incompressible fluid, okay, then the flux of V, the right side of the equation 1.56, is the total amount of fluid passes out through the surface per unit time. Okay, the total amount of fluid passing out through the surface per unit time. Now, the divergence measured the spreading out of a vectors from a point. A place of high divergence is like a faucet pouring out liquid. And if we have a bunch of faucets in a region filled with incompressible fluid, an equal amount of liquid will be forced out through the boundaries of the region. In fact, there are two ways we could determine how much is being produced. We could count up all the faucets, recording how much each puts out, or we could go around the boundary, measure the flow at each point, and add it up all. You get the same answer either way. So this is integral measured within the volume is the flow out through the surface. Thus, in a sense, is what the divergence theorem says. This is what the essential features of the divergence theorem. And you try to work it out with the number, confirm it, yes, this works well for a given V, and we can understand all about the divergence that's going to described as a fundamental theorem of a divergence. What is that? This is very easy to do it now. It's given here V, That's what your main vector here. That is what diverging. Okay, and during divergence, we calculate volume with the gradient and line integral on the surface. That's what the connecting relations. Okay, let's see. V is this. Del dot V can be found easily because this is a vector and this is also a vector. Take a del dot V. If I take this, I'll get a 2 into x plus y. Okay. Now find out volume integral now. 2 into x plus y d tau. This is dx, dy, dz. 0 to 1, 0 to 1, 0 to 1 because it says for the figure 1.29. Where is it? This is the 1.1. And there is a 1 unit along x, 1 unit along y, 1 unit along z. That is the volume occupied by this. It is a sort of a cube with a 1 unit of side. So therefore, we are going to find out integral x plus y d tau over this range 0 to 1, 0 to 1, 0 to 1, dx, dy, dz. Find out each time 0 to 1. This is the result. Next one, third one. Then put all of them together. And then you have the del dot v d tau, which is going to be the value 2. That is what the result that you will be getting by performing this triple integral on the left hand side of the function 2 into x plus y. This is the number. You can recheck, confirm it, make sure that these numbers are right, because we know that this is a simple integral. Perform this dx, dy, dz. One by one, it has to be performed. Total number you are getting it at 2. Okay, now what you have to do, what that we have found is the del dot v d tau. This is the left hand side that has been found. And what about the right hand side? This is where you have to understand about the integral surface integral v dot dA. Please note dA is a surface elemental vector and v is the vector what has been given here. This is a vector, and what is the surface vector here? It is dA 1. That is the surface 1. That is the surface 1 on the, it is towards you, okay, along the x direction, x cap, which means v dot dA with the dx dy, I have an x cap along this direction. This is the area vector which is pointing along the direction of x. Get the point? Y square dy dz. Look at this. This area is dy dz. What happened? Sir, நான் மீட்டிங்ல இருக்கிறேன். ஒரு 4 o'clock அப்படி கூப்பிட்டுமா? Okay, right. Right. Okay. Okay. After 4, I'll call you. Okay. So, what is that? Where are we now? We are here now. V dot dA along the direction of x, where you have a dy dz. Then the surface integral 0 to 1, 0 to 1. Y square dy dz. This is 1/3. Agree? I hope it's clear for all of you. Is that clear?
Yes, sir.
V dot dA next. On the opposite side of that, that is the minus x direction, which is again dy dz is the surface element. Dy dz minus 1/3. Okay, similar to this, same integrand, y square dy dz. Therefore, you are safe. You are getting the same magnitude. Doesn't matter for us, but we should be careful that when you multiply things, it cannot happen all the time for all the surfaces having an equal magnitude in opposite direction. Please take care of that. That should be handled carefully. Okay. So v dot dA for the x direction surface area element has been considered and it's over. Then come to the third one along the y direction, and this surface element is dx and dz. This is the z direction, and this is your x direction. In perpendicular term, that is this y direction. Therefore, this surface area is the surface element dx and dz. Dx and dz. Okay, and v dot dA should be found correspondingly. Okay, considering the y direction. Okay, this is the element. Okay, that should be found carefully. Then substitute the limits of the integrals and make an integration. You get 4 by 3. Opposite side. Okay, same dx and dz, but you see the function get changes. So be careful about what is happening with respect to that, and make a change accordingly, and then find out the integral, which is going to be minus 1 by 3 v dot dA, because v dot dA, and then make a substitution properly for the x and y's, and then simplify that. Should be careful about handling these things by looking at the x and y contributions and their existence. So this becomes minus 1 by 3 for the opposite side of this. Okay. You know why this is happening? What happened to the x? 2x to d dz. What is happening? Why there is a z square alone? Anything? That is where you have to think. Okay. So this is what, see, it's here it is same, but it's getting modified. Minus 1, 3. So x component is not been seen. And what could be the reason for that? When you find out v dot dA, this will be disappearing. Similarly, v dot dA, 2y dx dy, and v dot dA on the other side, which means dx and dy. Look at that. This is fifth one, the sixth one, and the area that is perpendicular to that is this dx and dy. See here dx and dy, and this is going to be 0 because the dot product of v dot dA. It has a finite value dy, it makes a contribution. Add all of them. That's going to be 2. That's the beauty of this. And you can see for this vector, if I apply this fundamental theorem of divergence, left-hand side of the volume, and whatever you get it in the over the volume is equivalent to the things that are coming out of the surface bounded by this volume. That is what the meaning of this fundamental theorem of divergence. Okay, and this has been worked out. The same problem, hopefully. Yes, y square, 2xy z square, 2xy. Okay, just go through that. And simple substitution has been done, and finally it has been shown that is consistent with what has been done here with the integrating, taking a divergence. So the dot products has been done, divergence has been done. So see, divergence has been found. 2x plus y integrated, that is 2, done. Then you have dot products everywhere and integrated. Okay, then you add all of them, sum. Over. Sure, this is also right, this is also right. Very happy to see that whatever we have tried to understand, struggle that has been implemented much without much difficulty. Take a divergence of x, y, z. This is the vector v. Divergence is this. Integrate that. X varying from 0 to 1, y 0 to 1. Done. Then take the dot product for all of them, whatever you require, all the 6 surfaces. See, has been found. Then perform the integration. Sum it. Well, you have the answer. So, whatever I explained has been implemented through Mathematica. You have another problem, same thing, but instead of having a 1 unit of cube, there is a 2 unit of cube. It's repeated. And it's not a difficult thing at all, because already we have done it for one case. Just copy and paste and change the limits alone, and automatically you'll get the result. Okay. I hope it's clear for all of you. And this is what your fundamental theorem of divergence, and it's also called Gauss theorem, which is used in a number of places. And then it's also called Green's theorem also. Super. You can have a clear-cut picture about what is this fundamental theorem of a divergence. And look at the fundamental theorem of a curl, which is a Stokes theorem, which is connected to the Stokes theorem. Fundamental theorem of a curl, which we, after looking at geometrically and performing this, you really feel that yes, this seems to be very important, and it's very simple also. Look at this one. Fundamental theorem of a curl, which goes by a special name Stokes theorem, states that, again, follow the first similar to that. As always, the integral of a derivative, here the curl, is the derivative, but it happens to be curl, that's all. The previous case happens to be divergence, that's all. That's also derivative. So, as always, the integral of a derivative, here the curve, over a region, here a patch of surface, yes, there's a patch of surfaces. The picture is given somewhere. Yeah, it's a patch of surface. Small patches. Okay, so integral of a derivative, here is the curl over a region, here the patch of surface is equal to the value of the function at the boundary, which is the boundary. Here, the perimeter of the patch. So many small patches are there, and I put them together, there's going to be a perimeter for that. That is, you go around that. So, surface integral connecting to this, like closed path, like boundary, close the boundary. As in the case of a divergence theorem, the boundary term itself an integral. The boundary term, specifically a closed line integral. It's a closed line integral. Okay, as always, the integral of a derivative, here the curl, is getting repeated. Okay, I think that has been copied again, doesn't matter. Geometrical interpretation, we look at it. Okay, so the geometrical interpretation, recall the curl measures a twist. Twist means rotation, twist of a vector V. A region of high curl is whirlpool. If you put a tiny pedal wheel, there it will rotate. So we would like to quantify that. What is the mathematics? That something is rotating. Is there any mathematics that's available? This is the mathematics. This is available for us to quantify that. So the curl is available. You put a tiny pedal wheel there, it will rotate. Now the integral of a curl over some surface, or more precisely, the flux of a curl through that surface represents the total amount of a swell. We can determine just as well by going around the edge and finding how much the flow is following the boundary. Figure 1.31. Indeed, this integral over the closed path V dot dl is sometimes called the circulation of a V. This is what we are trying to say. There are small patches, you add all of them. That is equivalent to the value at the boundary. That's what it means. Okay? This is what actually meaning of this mathematical expression. Okay? There are small things. And you add all of them. That is equivalent to the line integral of a closed path. That's what it means. Okay, now there are plenty of surfaces, infinitely many, that share any given boundary line. Twist a paper clip into a loop and dip into a soap water. The soap film constitutes a surface with a wire loop as its boundary. If you blow on it, the soap film will expand, making the larger surface with the same boundary. Ordinarily, a flux integral depends critically on what surface you integrate over, but eventually, this is not the case with the curl. For the Stokes theorem says that integral del cross V dot dA is equal to the line integral V around the boundary. The latter makes no reference to the specific surface you choose. So you can have a corollary here. Del cross V dot dA depends only on the boundary line, not on a particular surface used. 2 that del cross v dot dA equal to 0 for any closed surface, since the boundary line, like the mouth of a balloon, shrinks down to a point, hence the right side of an equation 1.57 vanishes because it's going to be a point, therefore that goes to 0. These corollaries are analogous to those of gradient theorem. You will develop the parallel further in due course. This is what the meaning of this fundamental theorem of the curve, and it's quite interesting to see that. And you can cross check it now by taking the special case of the problem like V is this. Find out the curve. This is the curl of that, and dA is known because here already you have a dA here. Okay, dot dA. So that dA should be taken, and then see for this problem, suppose V is this, check Stokes theorem for the square surface shown in the figure 1.33. So which means this is the surface which you are going to have, and the boundaries are 1, 2, 3, 4 together. So find out the del cross V dot dA, integrate over the surface, that's equal to line integral around a closed path. So this is what the thing that's going to happen. dA, del cross V dot dA, integrate 4 by 3. Now we start from here to here, 1. Okay, this is what your V dot dl, V dot dl integral 1. X equal to 0, y equal to 1 for the second path, and apply that V dot dl again, use them, get the result. Repeat here again for the third one, 4, add them. That's what before by 3, what you're having here. So therefore, you are sure that this equation is right. Whatever which we described perfectly right, and it works well. So theorem is right. So here is the, what did I do? 4z square minus 2x comma 2z. What is it? This is something else. Okay. Vector plot of something which I have shown. Okay, suppose v equal to 2xy plus 3y square. That yeah, this is what the problem. Check the Stokes theorem of a square surface of unit size. Okay, that what I have described here in this text, material has been reproduced here by performing using the Mathematica codes. That's all. And there is another problem probably that has been taken again. That has also been given here. Made effort to this to understand, and that has been done here, following the steps. So therefore, this is quite interesting to learn this fundamental theorem. They are very much strongly connected to the derivatives. Okay, so that's derivative for different forms. That's all. This is what you are. So of course, this will be used in a number of places. Here is the typical thing. Everywhere you have a del is involved here. Okay, and one typical example which I felt I can share with you in an electric field. Yeah, you want to have any clarification here? Doubts? Any clarification? Okay.
No, sir.
Yeah, any questions? No questions? Please go through them, practice them, do some of the problems other than what has been given as an example. That's most important. Okay.
Okay, sir.
That should be done. And you are sure that now all the three fundamental theorem, wherever you come across, it is easy for you to get the feel, yes, this is what really happening. And you connect the volume, surface, and the line properly. I have all the three fundamental theorems. With the proper integration, this was called with the gradients. So you have a divergent as a gradient, curl as a gradient. That's all. Okay. I'll just show you that. One of the things I felt I have something to show you. where is it? Dipoles in an electric field. That's very easy to do it. But only thing, instead of showing in a one particular direction, we incorporate both x, y, and z, like what we have seen so far. Okay, electric dipole. Two electric dipoles are opposite sign, but equal magnets separated by some distance. This is called an electric dipole. Create a plot showing the field lines and equipotential from such a system going to a distance of several times the separation of the charges. Okay, it is easy to write down the equations we need. If you assume the charge lie on a z-axis separated by a distance d, then we can write electric potential as this is the electric potential, where the magnitude of the charge and other overall factors are irrelevant for the figure we are to create. The electric field is now, see, potential is given. I'm taking the gradient of that and gives an electric field. Okay, d equal to 1 unit, and you have a r positive or negative positions, which is x, y, z minus d by 2, and r negative is x, y, z plus d by 2. So you take a potential which is equal to 1 by square root of that. Rp dot Rp minus 1 by square root of Rn dot Rn. E is the gradient of the potential V, x, y, z, and that has been found. This is what the result I have. Now I want to plot the potential and electric field together and show it on the picture now. Taking that one direction equal to 0, make a stream plot, which is a vector plot. Nicely you can describe this is what your positive charge and negative charge, and this is the field y equal to 0 remaining in the plane of x and z. And so beautifully. And with the potential here, which is the potential also being plotted here. Yes, it's also contour plot the potential, where you can move on this without doing any work. It's an equipotentials. Charge can move on that without doing any work. Okay, that's usually equipotential surfaces, and that is shown here along with the electric field, which is clearly shows that your potential and electric field, all the places are perpendicular. Okay, so you can see that very well. It's normal, and this is the equipotential surfaces, and this is the electric field, which is from the positive charge and negative charge. That's simply plotted by taking this gradient of this potential. This can be shown in 3 dimensions also with the vectors showing that you can see the constant surfaces here. Instead of in the plane, you have the equipotential line, and this is equipotential surfaces for the given dipole. This is what the dipole results, which is quite interesting to see how this.
So that inner circles are equipartitions of
equipotential surfaces. So if you make it in a plane, you will get this is equipotential lines. Okay.
Yeah.
3 dimension, it is going to be equipotential surfaces, which means this surface charges can move without doing any work. That's what it means. Okay.
Yes, sir.
So that's the E dot dl goes to 0. Integral over E dot dl.
On the top there is a cut.
Yes, that's also equipotential surface.
Okay.
That's also in the bottom. And this still that if you wanted to expand this, and then maybe that will get close at that particular point. Okay, because field strength going down, no?
Yes, sir. So
therefore that work then also it will be getting reduced. So if you are going radially outwards, okay, you can see this is what the thing that's going to happen. Your magnitude of the potential will go down when you are going away from the center, is it not? Potential magnitude will go down. If you are closer, field is more, then the potential is more. Okay, so all this can be visualized and you can feel it. Fine. I hope this is clear to you, and maybe you can spend little time to go through them, get an idea, and check whether these expressions are coming out properly or not. Okay, so now come to this dipole. When you place it in an electric field, they execute a simple harmonic motion. That also can be shown. This is the simple thing that can be shown, that consider a dipole oscillating in an electric field. Then it is at an angle of theta to the field. The magnitude of restoring torque on it is P e cos theta, sorry, sin theta, and therefore its equation of motion is described like this. Here I is the rotational inertia. For a small angle, the equation can be approximated to this. Sin theta can be written as theta, and this is going to be a time period of small oscillations. This is a function of P dipole moment, and inversely proportional to this time period is small h is inversely proportional to the square root of the dipole moment, electric field, and proportional to the I, which is the moment of inertia of the dipole. That's what happened now. One can clearly see that with respect to these variations, is the dipole, which can execute as simple harmonic motion. That's fine. Yeah. I can change the field strength now. And when I change the field strength, what is going to happen now? Small oscillations, so the period of oscillations inversely related. So it should go much faster rate. Okay. Getting closer and closer, and change the length of the dipole, which means you are converting the moment of inertia mode. It's going to be much faster now. Charge content can also be changed. Okay, and mass of this dipole can also be changed. And consequences, whatever you have here on this period of small oscillations, whatever is described here, it can be reflected here by changing each one other. This is initial angle is more. Okay, torque is experienced by this more, and length becomes smaller, and in case field strength also can be changed. You can see the number of lines that are there more and more. And you see field also brings the charges together also, which is effectively reducing the length of that dipole. Dipole charge can also be changed independently, and mass also can be changed. So mass change also has an influence because it's connected to moment of inertia I, and you can see that oscillation goes take lesser time. And this is what is given here is Pe by I. That's going to be omega square. So you can see that P must be, is it time period or a frequency? E by I. E by I. So this is a period of small oscillation. Yes, this is the time period. Okay, that class and influence, and correspondingly we would see that it changes. Frequency will be getting modified by the effect of charge content, mass, and then the distance between this dipole. Okay, all has an influence on that. Please note, and also initial angle. Okay, very small oscillation. You see the initial angle. If I change it, it increase. You are giving more energy to the system, or a force that oscillates. Torque experience is more. So length has also influence. So every parameter, whatever is observed here, has an influence on the time period that can be clearly seen. Okay, and which means your electric field also going to be oscillating. And there is a field which is there, and this charge is moving within this. So therefore, there's going to be electric field which is produced by this dipole also will be getting changed. So these are some of the important observations that takes place by the electric dipole. This will be extremely useful for us to understand about the dynamics of the dipole in a molecular level. Okay, so this is what the thing which I felt and be describing it. Fine now. I hope this will be useful to you. I will send you these things to you to go through them.
Yes, sir.
Then enjoy this dynamics which is described here. Okay, so this is all about this 16. Two of them are completed, and therefore Gauss legendre, of course, del operator overall. Okay. Now, I think I have not touched this Rangagote method. This has been done in the class already, or derivation?
Yes, sir. Derivation has been already took,
What about
in
the
the class.
programming part? The clarity
Programming they have done using Fortran. We have done using.
But that till now, that do they get any clarity on that?
Yeah, that some conceptual clarity maybe.
Yes, it's not possible. Now I'll explain to you now. It will be very, very easy to do it in Mathematica. Huh? Okay. This is the formula, right?
Yes, sir.
Fourth order RK. You can see here K1, K2, K3, K4 are connected with this H parameter with the function x0, y0, and then there is a H parameter goes to the next level to find out K2, which is just changed by x0 by H by 2, y0 by K1. This fellow comes and sits here. Okay, this fellow
Yes, sir.
comes and sits here. When you are coming from here to here, this fellow will come and sit here.
Yes, sir.
When you come here, this fellow comes and sits there. And here you are x0h and y0 k3. And here again you have x0 and y0. So this is k2 and k3 where there is a link with respect to k1 and k3, the last one. Y1 is given by this y0, 1 by 6 of this, which is multiply weight factor 2, and there is a weight factor, another common weight factor. If you write it, in fact, it will be K1 by weight factor of 1 by 6. This is 1 by 3rd, this is 1 by 3rd, this is 1 by 6 again. That's what the meaning of this. This is what the basic formula, right? But understanding this and how do you use it with the Fortran, and you are going to repeat the iterations again and again. And now you will see with Mathematica what happens. It becomes the simplest. Okay, 4 or 5 lines. That's enough. And we can produce these things K1, K2, K3, and Y1 for a given value of H1. Then go to the next. You can confirm yes. There's an iterative procedure that's possible. That iterative procedure can be implemented on the one step what you write and make it as the statement what you have learned already is called a nest listing. Find the first one, take the input to the first one, get the second one. Go to the third one, take the inputs from the second one. Repeat, you will get the result. So one Rangagote step is this. Repeat it for n number of times by using a nest list. That's all. That is what your technique that should be used when you use Mathematica. Okay, let's see what is the, you will give with the number problem so that you are sure that what you are trying to do is consistent. Correct now? This has been done already for a given problem. The first step, when, look at this problem now, find y of 0.2 for y prime equal to x minus y by 2 with y0 equal to 1 with step length 0.1 using a Rangagote 4 method. Okay, this is what usually problem will be given for students.
Yes, sir.
Such problem will be given. They will be struggling to understand and doing it. Now, y prime is this, and substitute these formulas step by step, whatever is given here. That steps are given detailed for every one of them. K1, make a substitution, find out the first one. K2, make a substitution from this K1. substitute, simplify the number. K3, substitute this number, be done. K4, do it by K3 and get it. Then sum it. Find the product and make a sum. And this is what the value of the y1 for the first step for y of x1, x is equal to 0.1. This is the value that has come for this function. Now, 0.1 has been found. Y of 0.2, I have to repeat the process. So now asking xn by 1 in the place of x0 by 0. Repeat the process. Right? Start from xn by 1, find out the number. Take this k1 here, find out the number. Take the k2 here, find out the number. And see that x0 and y0 becomes xn y1. Okay? So which means previously calculated computation has entered into this, is it not? Okay, and substitute it, and I'm getting the value of the 0.2. This is the y of 0.2 is this number. Okay. Now, if I go to the third one, so what would happen? This will be x2, y2, and x1, y1. Repeat. Then fourth, fifth, sixth, go on. And if we can write a program, then that will be easy. So one Rangekutta step is this one. If I wanted to go to the next one, what you do, because these things are going to an input for that, that input can be achieved by just adding what you call this nest list. Take the previous result and put it into the first calculation. Take to the previous result, put it in the first calculation. That can be done by adding a number n, which you would like to repeat number of times. So one step is these are the variables which are defined here, that question input. And for a multiple steps, add this n and make a nest list of one step, n number of times. Okay, if I do that, I have the result. Okay, let me check now the first part of it. I'm taking the output also here. Print out K1, K2, K3 so that I can confirm that K1, K2, K3s are produced. And then I'm getting its number y of 0.1 also. So to start with, I'm having this. And later on, I don't want to see this again because it's going to be a large number of data that will be printed when you go for a larger number of n values. Okay, so to start with, let us have this and confirm that one step is working properly with this pattern which you have written. Then if I add the another alternate, that number of steps that is to be needed for iterative purpose, the next list, you just add a number n with the same variable that goes into this. Okay, let me try to see this. As a first step, what you have here, this has been done. This has been written in this form. Expression, your variable and initial values and dt. This variable can be anything because we are putting it a variable with a delayed equal, which is we are making it. Therefore, this variable names can be anything. It can be dt, can be x or y, or these are all options that you have. But we try to keep it in the consistency purpose like this. And then you have make a small module where you wanted to find out k1 dt times this to start with. K2 is, you can see threading with the variation, that's the one which is going to be plus k1 by 2, and we are threading it. The thread will be taken care to take the previous one to the present one, previous one to the present one. Okay, that is being taken care by this. And we'll define this as a k1, k2, k3, k4 and print it and get it. Now this can be implemented by just simply enter this. This is done now. And I am taking this example. Let's take this one Rangekutta step. And the expressions, you have this, first one is this expression, x minus y divided by 2 to start with the value equal to 1. This is what your equation here, and xy is the variable. This is the initial condition. Steps of 0.1. If I enter this, say, one iteration over for a x is equal to 0.1, I'm getting the number 0.95368, which is 69. Okay? 1, 2, 3, 4, 5. And check the other values. Minus 0.5, minus 0.5, minus 0.04625, 0.04625. 0.04634, that number is also available. 0.4268, done, over, this is enough. Okay? So
Yes,
get
sir.
convinced now? Sure that we are getting it.
Yes, sir.
So, but how that's been implemented, one step is there, in which I'm just adding for a 0.1 of x 0.1, I wanted to find out, and all this has been given. Okay, equation also has been given. The solvent is given. One step again ahead, there I'm going to use 0.2. Okay, check it. So add this, implement. The answer is 0.91451. I have it. This is 0.2. Y of 0.2 is this number. And reconfirm whether the K's are right. 0.04268. Whatever. Numbers are different. So we have to check now. Implement here. So we should use that numbers. Sure, that should happen because there should not be any ambiguous thing on that. Okay, let's try to check the numbers. This is x1. Zero 0.41451 is right, but what about this numbers? 0.04268, that is not there. So we have to check now. 0, 1, 0.2. One step each time, it should be done. Come on, this is the answer is right, but why the numbers are not right? How does it possible? 2, 0.1, 0, 1, 0.2, 4, 1, 4, 5, 1. That should be with these numbers that should happen. So numbers are modified. 0.2, 0.1, then 0.2, 0.085. No, it's also not correct. But the answer is right. How come this is happening? Okay, we have to check that. Anyway, I just go through it one more time here. Final answer is right, but the numbers what I'm expecting that should happen. This is for 0.1. Then this is for the next value that should start with the initial value of x1, y1. Okay. But it is calculating properly, but for calculating x1, y1, point 2. Well, so I think I need to have some attention here to get this in between values of K1, K2, K3, and K4. Print values. dt. One more time. I enter here. When I wanted to find this, one step, x minus 2. Function is same now. Here, what are I have? X minus 2, x comma y, 0. Only thing I made a dt becomes 0.2. Okay. Okay. One minute. Just check the other problem that I have. The intermediate steps, whether that is coming out properly or not. Because here's the another example. We'll see. But anyway, we'll assume that this is rather right, but we'll cross check these numbers in between numbers. Okay. So this is the next part of it where you could get it. The final value point 2 is 91451. That is coming out well, but in between value there is a problem which we will confirm it. Okay. Now here, without the print values of K1, K2, K3 for 2 n equal to 2, which means 2 iterations, where we are writing Angakutta for the system of equation, that same thing, x minus by 2. That system will come here. This is what your system, x by 0.1 to 1, 0.1. This first iteration, that's the number. This is 2 iterations, second. I think there is something which is happening in between. We have to check it now. Let's see. Because the previous output should be available for the current one. That's not happening, but at the end result that is happening now. Anyway, we will check it now. So now, in this case, we are not writing this output K1, K2, 3, but we are directly looking for the solution by iterative manner by taking first iteration is this number is right. Second iteration number is also right. Both the results I have 953688 0.914512. That is also right. Okay. Do this mathematical with numerical solution. You have the end is solved, interpolation, check it, check the number. Okay. 9536 double number and 914512. That number also you are able to get it. And you can go up to 1.2 instead of 0.1 with the interval. Calculate and then make a data points here. Okay, that is also done. Look at analytical solution here. This is what the analytical solution for the equation what we have solved by using a Angakutta. Okay, and make a plot with initial condition y0 equal to 1 that has been given there, and this is what the plot. This is the data points. Look at this, both will be consistent with that. Okay, this is example 2 here. Let me try to check whether the numbers are available to place a first step before I execute it. So let me take, this is the first set of data which I have. I just copy there and compare it with this first set of data that I have here. Here the function is y prime equal to minus 2x minus y with the initial condition minus 1. And I wanted to check whether these numbers are right here. 0.1, 0.1, 0.085, 0.8575, right? 0.071, this is right. I want to check the second set of data. Where is it? This is the second set that is being generated. Go back to that second point. This is the second point here at y equal to 0.2. I wanted to confirm that. Otherwise, we have to look at carefully what is the problem. 0.07145, fine. 0.0587879, that's also right. 0.5856 is right. 56 is right. Then 0.0456, that's also right. So there must be some silly mistake that we are making. So these numbers are correct now. Whatever I have generated for 5 different points, all of them are consistent. You can see here these points have been generated and you have given the final value also. Okay, for 0.1, 0, 0.1, 0.2, 0.3, 0.4, 0.5. This is consistent for this function. Same thing should happen there also. Maybe I think you have to do it at that time and then look at the results. Instead of doing it independently like this, I should do it by second iteration separately, this one. So therefore, going to be an issue. Probably if I do that independently, maybe I will be getting it. Anyway, we'll check it now. This has been done here with an output of this K1, K2, K3, K4. Then without the K1, K2, 3 result is been given here. Okay, it should work. That's directly you are getting the result. And this is what the result that you have. These numbers are reproduced from there. You can check with numerical and analytical solutions. Confirm it. And you have the nonlinear van der Waals equation. This is the result. It's very easy to do it. Just change this. System is now this. You can see this is dV by this can
That
be
is second order differential equation.
that can be converted into first order form.
First order, okay. Yeah.
First order form, and you have the variable here that epsilon is 0.5, and then other things are fine because you have to reverse it because it's equal to, if you write it, it is going to be change of sign, and v will be there for x dot, and minus x is this one. Okay, and some initial conditions are given here, and you made a plot, and that should work without any difficulty here. This is what the results that you have. This is the van der Waals equation, and we can see what is happening when you take it to a smaller value, 0.1. That epsilon will become smaller. You're coming close to the circles, decaying circles. Why not? You're coming closer and closer, and it will become a sort of a simple harmonic motion. Okay, this is what will happen. When this is small, it is equivalent to having a simple harmonic motion. Okay. Similarly, you can try this other equation. This is the so-called Duffing equation. X minus x cube. You can try here and change the parameter of this epsilon 3 instead of 3, various values of 3. You can try with the Runge-Kutta sign. You can see that what is the thing that is happening. This is all possible, and I think there is a period doubling. There are many things that has been done with the help of these things. Okay, so this is all about your Runge-Kutta method, and this clearly gives an idea about how to implement it very comfortably without having any ambiguity. Right for one step, do it for the nest list for n number of steps, that's all. And that implies that you are going by each one step now from here to the next, to the next, to the next, to the next. Every step that the previous result is being used here. For example, when you are coming here, you see x4 corresponding y4 when you want to find, you are replacing that here. x0 is replaced and 3 will be used. x4, k1, k2, k3 with respect to this. x0, y0 is replaced by x4 and y4. Okay, this is how it goes on. Okay, so therefore this is x3, y3 replaced by x0, y0. Here it is x2. This is the starting point. This is x1 and this is starting point. That is done by using this write one step and do it by the so-called nest list, which is you have learned already by using Mathematica. This is a Mathematica code to bring out that kind of a nest list. Do it on the one step Runge-Kutta, then it will be possible for you to get the result. Okay, so you have cross-checked and it is working, and we are happy with this numbers. And I'll just check that alone. You can also go through them, then find out what could be the cause for that variation. Okay, stop here.
Okay, sir.
Okay, so again, tomorrow I'll confirm it by tomorrow morning around 9 o'clock because I might be having some work.